So one thing that we have to consider when we're is our columns and braces, and we'll look real quick at some examples. If we're looking at the design, say, of a column and a brace, and when we talk about the uh, uh, horizontal forming, in particular the columns and braces, or the columns are important. But what's important when you look at a column design? Well, remember, when we're using wood, you apply loads along the axis. Compression is parallel to the grain. All right. The capacity of the wood then depends on the cross-sectional area of the wood and the slenderness ratio, obviously, just like normal things we look at in structural design. And the allowable compressive strength parallel to the grain depends on the wood species and the grade. So again, we go back to the tables we looked at earlier for different types of wood, and that's where the optimal type wood or species comes from. And you can change the stress based upon the slenderness ratio, obviously. If you've got a thicker piece of wood, which changes the slenderness ratio, obviously there's a balance between the two. So remember, the slenderness ratio is the ratio of the unsupported length, the L, to member width of the face of the member under consideration. Okay. You've got to look at two values, right? Because for wood members, there's two face widths, right? A narrow one and a minor one. If the column's on brace, the controlling slenderness ratio, the larger one, will be the one determined by using the dimension of the narrower face, obviously. Okay. So for wood members, L over D can't exceed 50. And you can see in this case where we have a member and the slenderness ratio parallel to the narrow face is 48. The slenderness ratio parallel to the wide face, 20.57. The larger is the controlling, that's the 48. And this is for unbraced. And so it obviously, again, it's obvious that the narrow face is going to rule. If the column were unbraced and 7 feet long, the controlling slenderness ratio would be over 56, or would be 56, and that'd be over 50, and you wouldn't want to, and you couldn't permit that at all without somehow modifying it, and that would be by using a larger member section or additional lateral bracing. All right. Again, if you have a lateral bracing, and you calculate again the slenderness ratio, and you'll see that the 16-foot total is broken into two sections, a 7-foot section and a 9-foot section. The slenderness ratio parallel to the narrow face is 108, or the 9-foot dimension divided by 3.5, which is the size of that 2x4. Remember, the 2x4, the 4 isn't 4, but it's just over 3.5 inches. So in that case, you'll see that the slenderness ratio parallel to the wider face is 34.9, to the narrow face is 30.8, so the controlling slenderness ratio is 34.9, right? The brace just brings those numbers way down. As you can see, you'll move the brace up and down to fit where your whaler locations are and other support members. Part of that is just how you manage to work through the job site, isn't it? Lateral pressure of the concrete. Remember, and again, look at the programs. I encourage you to go back and look at the programs, because as I mentioned, that's what we're going to be looking at it in terms of the final and some questions further on. Lateral pressure of the fresh concrete, and that goes to how long the concrete placing operation is going to be. loads imposed by fresh concrete against a wall or a column, they're different from the gravity load on a horizontal slab form, that is after the concrete is hydrated, it's solid. The fresh concrete behaves at least temporarily like a fluid, so you get hydrostatic pressure laterally on the vertical forms, and it's as if you got liquid head. So again, once the concrete hydrates, the force goes down, straight down, as a gravity load on whatever footing you have. So with a slower rate of placing, concrete at the bottom of the form begins to harden and the lateral pressure is reduced. So again, go look in the program and you'll see how the numbers start changing. In particular, the number of components, given components in a form, the number of studs, the number of whalers, changes as you increase the time period over which concrete is placed. In other words, the slower you go, the longer the pour. The slower you go, the longer the pour. When you go slow, the concrete at the bottom of the form is hardened by the time you're done. But what that does is it means that the concrete down at the bottom of that form behaves as just a gravity load, and you have less concrete acting as a fluid. So the weight of the concrete, the rate of placement, the temperature of the concrete, whether you use any admixtures or retardants, and how much vibration all affect that lateral pressure. And you'll see, again, go look at the program in particular, you'll see weight of the concrete, rate of placing, weight of the concrete, rate of placing, vibration, and temperature are all items that are variables for us. Okay, a little later on you'll see, and there's a table in the handout that shows maximum pressures that you can use for design of wall forms with rates of placement up to 10 feet per hour. Okay, which is a fairly high rate of placement. So before you start your form design, you need to look at a number of things. What are they? Job conditions. You need to look at the site, how you plan on doing the work, the kind of equipment that's around there and you'll be using, especially for the equipment placing the concrete. The temperature, we talked about that. The tolerances you have in terms of deflection. Again, you don't want bulgy or bowed out concrete when you're done. And there'll be tolerances that you have to deal with. Access to the site in general. It's important to know the knowledge level of the workers. You know, how well they can do their work, how experienced they are. Skilled workers can be more efficient in placing the concrete, how they deal with the forms and reuse them. If you have less skilled people, you're going to look at a different type of form system. Okay. What kind of materials you're going to use. Plywood, the lumber sizes, the hardware that's available. Okay, and so you're going to, all of these things are going to change the efficiency and the again, the kind of wood in particular, obviously, and you'll see that's one of the first variables we look at on the spreadsheet, is type of wood. The strength of that wood, or of the form, goes directly to the kind of tree the wood comes from. If we look at the design load, we need to know the design load for the concrete form. Okay, and again, design loads we mentioned before is dead load. Dead loads, you can see concrete and rebar go between 130 and 160 pounds per cubic foot. Any type of embedments that you have. You have to consider the form work, which you should consider at least 10 pounds per square foot. Okay. Live loads, you need to look at a minimum of 50 pounds per square foot. And if you're going to be running carts, carry some concrete around on that site, 75 pounds per square foot. The number of people that you'll have out there, the other types of equipment, the impact that comes from that live load, you know, what kind of things are going to be dropped on those forms. So you need to look at the combined dead and live load. It's going to be a minimum of 100 pounds per square foot, or again, if you have carts, 125 pounds. You need to look at lateral loads. And for slab forms, you have to look at the greater of 100 pounds per lineal foot of slab, edge, or 2% of the total dead load. For wall forms, it's the greater of 50 pounds per square foot, or there may be local code requirements from the building codes. There'll be wind loads. Okay, and in particular, for wind loads, you're looking at 100 pounds per lineal foot of wall. If you've got wall that's greater than 8 foot tall. Together, those will give you the design loads for the concrete. For the wall form design, again, we've been talking about this. The pressure imposed by the concrete on the wall is a function of the density of the concrete, again, the weight, the temperature, how fast it's applying, and the height. All those items, again, you'll take a look at the spreadsheet. The pressure on the concrete will impose on the wall form is determined by the placement rate, and if the placement rate does not exceed 7 feet per hour, okay, the pressure in PSF is a list of the following, yet it's never less than 600 pounds per square foot. So, and again, I look in the notes that you'll have in the formula. I think are a little clearer, and you can check the calculations there. Know again, the main thing, it's never less than 600 pounds per square foot in terms of the wall form. If the placement rate is 7 to 10 feet per hour, you're going to use the least of the following values. But again, never less than 600 pounds per square foot. If the placement rate is greater than 10 feet an hour, you're going to assume a lateral pressure is equal to 150 times h, which is the height. So just some guidelines for you in terms of coming up with numbers for pressure of the concrete. Again, remember what they vary mainly because, again, the concrete, the higher you get, or the higher the wall, the more concrete, so there's more weight obviously, but again, the time between placing concrete at the bottom and the top is substantial, especially as the wall gets higher and higher. But that also means that the concrete at the bottom starts hardening, changes to just a straight dead load down, and there's less fluid load that you have to have bearing against your wall. But you can see by having the 600 PSF minimum, you always have a guarantee of where you can go. If you can do some less based upon what you're designing, that's fine. But or if you're going to have more, I'm sorry, it's just the opposite of what I just said. You're always going to have at least 600 PSF. And you have to keep in mind that if you're going to consider those pressure calculations, there's other assumptions. Concrete density is 150 pounds per cubic foot. You vibrate the concrete at the time of placement and not more than 4 feet below the top of the concrete surface. Okay, you got to keep moving the vibrator up. Why? Again, because it starts hardening, and if you vibrate into where it's hardening, you crack it. You just don't get the strength, and the concrete doesn't end up turning into that dead load that just applies downward. concrete has to be made. You don't have slump more than 4 inches. Type 1 cement, there's no pozzolans or admixtures into it. So it's normally setting concrete. And the concrete temperature is a range of 40 to 90 degrees. If it's less than 40 degrees, right, you don't get strength. If it's more than 90 degrees, you'll have problems with it setting up too quickly unless it's iced. All right, so temperature control is important. So you got a wall design, you've determined the pressure that we've already talked about. You can go through and calculate, again, using the criteria we just talked about, the pressure that that's going to be applied on that for that wall design, right? And again, table 5.4, and that's still coming up, but you'll have it in your printout. Will give you a guide as far as the remember, it has to be at least 600. In this case, for this first calculation, shows 712 PSF after we go through the calculations. Again, what you really want to do is see how close. You always got to have at least 600, and you want to try to keep from exceeding that too much. Again, the more the pressure, the bigger the form has to be. One thing you're trying to do is always trying to keep that form to some type of a minimum, not over design it. Again, there's another example of just determining the pressure given the concrete density, the height, the rate of placement 5 feet per hour, the concrete temperature 80 degrees. What you should do is probably go ahead and input, that's in the first tab on your wall design spreadsheet, and put those numbers in, and you should be able to verify that it comes out near to that 712.5 PSF. All right, so you might want to try doing that. Here's a table 5.4 we were talking about a couple minutes ago. Again, it gives you an idea based upon the rate of placement and the temperature, the pressure that you have to use, and you see here the 700 PSF is the minimum that governs. Okay. Then, as we were talking before, and this is a familiar chart, I think if you had hydraulics or soils, you'll see that this particular loading, and this is the loading we're concerned about, the concrete acts as a fluid, and it applies the pressure out on the sides of the form. So the idea is, if you place the concrete at a slower rate, the concrete starts hardening, and then it slowly, from here on down, starts being directed down instead of off to the sides. 712 is the number we've been calculating, and here it's the pressure on the forms pushing out. Okay, again, safety, isn't it? That's all we keep saying, safety. We assume loads are uniformly distributed. Remember, that's part of the thing that we have the concern, especially during construction, as you're placing that concrete, the loads aren't uniformly distributed, are they? So one of the things you try to do when building and designing is manage how the loads are applied to the forms, so that you don't overload the forms and cause a collapse. Remember, we were talking about members are looked at as beams. We're looking at this as all simple beam design, and when we have 3 or more spans, it's a continuous beam design. So, what are the typical components of forms? Sheathing, studs, joists, wales, stringers, shores, and tie rods. We've already looked at that a number of times. You could look at that again if you need. Compare it to the drawings that are here and that I've already posted for you. You have to be concerned with bending, deflection, and shear. And for formwork, the smallest value calculated for each category of bending, deflection, shear is the one that's used as the safe span. Okay? So in this case, you can see the formulas, and again, we're looking at the 2 and 3 span, and this is considered the continuous. And the formulas for calculating the deflection and the bending stress and the shear. Right. And again, I think what you need to do is look these over, be familiar with them, but we're going to use our programs to worry about that. Deflection, again, for simple beams, it's deflection limit to L over 360, which is a common number you'll find in all the codes. So you're going to be calculating the same way you normally do. You have to look at the shear of the, especially of the plywood that you're using. Remember that the plywood is a composite, it's made up, so shear is important. And there's a wall form design example, and I think what's important first is just to keep in mind the steps. First, you're going to find the lateral pressure. Okay? And again, there's table 5.4 helps you with that. You're going to look at the sheathing. And the sheathing, in order to look at that, you're going to consider the bending. Okay? And you're going to consider the deflection and the shear. And again, table 4.3 gives you some values for those items, right, so that you can use that. And you're going to do and calculate the spacing of the studs. Okay, and again, remember what's important about this. You need the strength to be able to deal with the material, but spacing of the studs is critical because the farther apart you can get them, the less material you need. So that's what's important. That's why I think, especially when you look at the programs, you can see how much quicker it is to be able to come up with a variety of stud spacings by varying material, thicknesses, size of members. And I think that's what is really important here, is to be able to look at some alternatives. As a contractor, you don't want to just look at one design. You want to be able to use something like the spreadsheet to give you 3 or 4 different designs so that you can come up with a cost for material, and by knowing the material, coming up with a cost for assembly or time, number of staff you need, number of crew. Now that's what's important, and you can go ahead and figure 3 or 4 different alternatives using the program and the time it takes you to do one set of calculations by hand. You're that much ahead because you have 3 or 4 alternatives that you can measure and evaluate against each other. So what I'd recommend is you take these numbers and put them in the program and see that. Again, you see by changing the size of the studs and the spacing, and you can change also the spacing of the whalers, the whale spacing. You see that again you're changing the amount of material that you need out there. So step 3 is when you're going to look at the stub size and the spacing of the whalers, and you're going to check the bending. Okay, based upon the allowable span. Again, based upon different types of wood, the shape of the wood members, you're going to be able to do all of that. You can check deflection. Again, if you look at the programs, you'll see tabs that check all of these items. So what I'd recommend is that you go through tab by tab and look at those items. And I'll talk about that next week too, so we will do that together. Don't worry about it. I want you to think conceptually about what's going on right now. Again, you can change the spacing of the wales, just like you can change the spacing of the studs. You can also change the spacing when you're looking at horizontal on the joists. Okay, then what you're going to do is look at the tie design and the tie spacing. Again, ties cost money, and they help maintain the dimensional integrity of the forms. So it's important that you look at the spacing, and if they're spaced too far, again, that's where you get bending, right? Then you're going to look at step 6, the bearing check, and that's the bearing of the studs and the wales, and the bearing between the ties and washers. And again, what are you looking for? Too much load, and you're going to crush the timber. You're going to crush the wood. So that's why you check on the bearing. Make sure you don't exceed the strength of the wood. Keep that in mind. Again, there's a tab for that, but you want to make sure that you maintain the integrity. Why? First, certainly for safety, that it keeps your form together, but more importantly, it allows you not to damage the wood, so you can keep using the wood over and over again. Then you look at the relationship of the bearing area between the studs and the wales, right? And then you look at lateral, step 7, lateral bracing. And struts, the same thing. Again, there is a set of tabs for each of those items that we will look at next week and go over, but I encourage you to again, keep flipping through those programs so that you're familiar with them, and we'll talk about those next time.